Limits at infinity, tips and tricks. So these are prerequisite skills that you might have learned, but also might not have seen used this way. And they're skills that are really helpful as we evaluate limits at infinity in just a couple videos. So when you have a limit as x approaches infinity of f of x that is equal to L, where L is a finite number, then you also have some sort of horizontal asymptotes. And this is something that can help us out because for some functions, we need to evaluate limits based on what we know about their graphs. So let's say we have the limit as x approaches infinity of e to the negative x. Well, you can either sketch out or imagine in your head a little graph of e to the x, if I can draw my x-axis, which looks about something like this, with our asymptote at y is equal to 0. And if we look as x approaches infinity, we see that e to the negative x is approaching 0. So it's getting smaller and smaller and smaller, but will never be negative. This can also be helpful with limits as x approaches negative infinity, say for the limit as x approaches negative infinity for e to the x. The graph of e to the x looks something like this. And we can see as we go to negative infinity that e to the x approaches 0, since we have that horizontal tangent at y equals 0. Now we have the limit as x approaches infinity of inverse tangent of x, which honestly I prefer the notation arctangent. So we have arctan of x. The graph of arctan looks something like this, where we have a horizontal asymptote at positive and negative pi over 2. And we go through the origin. And the shape of our graph, ooh, that's a little too curvy, looks something like this. It doesn't have to be perfect. We're just kind of picturing what the graph looks like in our head, or sketching a quick picture. And we can see as x approaches infinity, arctan, or inverse tangent of x, approaches pi over 2. Infinite limits of composite functions can be a little bit tricky sometimes. So let's look at this middle piece of this first. So we have the limit as x approaches a of f of g of x. And the innermost function there is this g of x. If the limit as x approaches a of g of x is equal to some value, so that is the limit exists, then this limit as x approaches a of f of g of x is equal to the limit as x approaches b of f of x. And this just means that you have to start by evaluating the limit of the innermost function. Much like if you had like f of g of 2, you'd have to find g of 2 before you could find f of g of 2. We have the limit as x approaches 0 of e to the 1 over x. So here our inner function is 1 over x, and our outer function is e to the x. So first, we need to find the limit as x approaches 0 of our inner function, which is that 1 over x. The limit as x approaches 0 of 1 over x will be equal to infinity, because our numerator stays the same value, but our denominator gets smaller and smaller and smaller and smaller and smaller. So much like if you have like 1 over 1/2, that's equal to 2, but 1 over 1/3 is equal to 3. So when your denominator gets smaller while your numerator stays the same, the overall value gets larger and larger. And now we can find the limit as x approaches what the inner function was approaching. So the limit as x approaches infinity of our outer function, which is e to the x. And the limit as x approaches infinity of e to the x is infinity. So the limit as x approaches 0 of e to the 1 over x is infinity. We have the limit as x approaches 0 from the right of the natural log of sine of x. So first, we have to look at the limit as x approaches 0 from the right of sine of x, which will be equal to 0. And if you want, you can think of this as equal to 0 from the right, because here we're looking at the limit as x approaches a value from the right. So now we can find the limit as x approaches, again, coincidentally, that it's actually the same, but 0 from the right of the natural log of x, which is our outer function. The limit as x approaches 0 from the right of the natural log of x is negative infinity. So when you have the limit that is, well, a one-sided limit of a composite function, that side that you're approaching is going to follow you along. We have the limit as x approaches 0 of e to the tangent x. Our inside function is tangent x, so we need to find the limit as x approaches 0 of tangent x, which will be equal to 0. And again, it's a coincidence that the value we're approaching and the limit keep being equal to each other. Now that we have the limit of our inner function, we can look at the limit as our outer function approaches that value. So we'll take the limit as x approaches 0 of our outer function, which is that e to the x. The limit as x approaches 0 of e to the x is e to the 0. We can actually use direct substitution here. And e to the 0 is equal to 1. We have the limit as x approaches 0 of e to the 1 over sine of x. So we'll need to start by finding the limit as x approaches 0 of that innermost function, which is 1 over sine of x. 1 over sine of x is equal to cosecant, so we have the limit as x approaches 0 of cosecant x. If we think about the graph of cosecant, then we have a vertical asymptote at x is equal to 0, where we kind of have these u's, where if we look at the limit as x approaches 0 from the right, we go towards positive infinity, and if we look at the limit as we approach 0 from the left, cosecant x approaches negative infinity. So that means that the overall limit does not exist. And because of that, that means that the limit of this overall function here also does not exist. If instead we had looked at the limit as x approaches 0 from the left or from the right, that might be a different story.